Okay, hey, good afternoon, everyone. Oh, I see there are a few more people coming in. Let's try and get started. My name is Roi Barkan. Hello, and today we'll talk a little bit about coroutines. As I mentioned, I'm Roi. I come from Israel. I live in Tel Aviv. I work for a high-frequency trading company called Istra. We do C++ cool stuff in the low latency sphere. And if you're interested in working for a great company in Israel, then feel free to join us. And I'm a happy learner. I try to be as engaged as possible whenever I attend talks. And please, I urge you, ask me questions whenever. And let's make it educational for all of us. Today, as I mentioned, I'll talk a little bit about coroutines, but I'm going to take a sort of like a high-level view of it to try and give us a little bit of intuition of what this feature is in terms of when we can use it, why we want to use it, and how it's like. We'll do a little bit of history, a little bit of understanding of the basic terminology in the C++ language of coroutines, and then we'll spend a lot of time going through quite a few different scenarios where coroutines typically come into play. Also spend some time on anti-patterns or things where people sometimes use coroutines and I think might be more of a challenge than a benefit, and I'll also be happy to hear what you think about those things. Let's start off with talking a little bit about when do we think a language feature is useful for us and what for. So as you know, C++ language supports a lot of paradigms, a lot of types of systems. We have publish, subscribe, client server. We have data flow systems that do like data-oriented programming styles. We have even lower level idioms like RAI and range-oriented programming, etc. And every language feature typically lends itself more or less to these typical types of uses or to these typical types of systems. And so, for example, concepts, they are mostly looking into compile time dispatch, and short pointers are meant to help or can help a lot when you have like an object-oriented object graph sort of type thing. And you would typically use range adapters if you want to do like a stream of data operations on information. And what I'd like to try and answer together with you today is which system designs can benefit most from coroutines, okay? Some might consider coroutines as an implementation detail, something that's very low level. Others think of them as really like high level architectural structures or constructs. And we'll talk and see where we can see or fit coroutines in this mix. And another important thing about coroutines and about using or adopting them is to try and understand how viral they are. If we have a code base and we want to try and start introducing coroutines in there, will it be something that typically can be constrained in one single component, or is it something that might spread out? And if it does, will it spread out of control? At the end, you should probably get a sense of what are cases where coroutines can be used to make our systems a little bit simpler, or maybe a little bit faster, or maybe a little bit easier to maintain. So a little bit of analogies of such cases are, for example, if I'd try to look at STL containers, they're obviously like high performance data structures. They're very, very easy to use, but complicated to implement. Happily, the compiler vendors implemented them for us. And they work great if we have like very large collections of information, typically of like value types or algebraic value types. Similarly, lambdas, they can be thought of as like a syntactic sugar. Like a lot of things that can be done with lambdas could also have been done without them, but they really simplify our code. And the main thing that lambdas give us is more locality of different different code snippets that actually run at the same time or in relation to each other. Can also be placed in the source file in the same location, whereas before lambdas, they had to be split up. And ranges, another example, it's a very, very simple notion, but with a very, very complicated machinery under the hood. And once it got introduced, it really enriched our vocabulary. We started talking about adapters, views, sentinels. We started thinking about algorithms that compose, and that really enriched our experience. But still, it was most suitable, or it is most suitable when we have like data-oriented, one-dimensional systems or processors. Okay. So what about coroutines? So one thing that we should know, or that I really want to stress, is that coroutines really add like a new section to our dictionary, to our vocabulary when it comes to design. When we talk about coroutines, we'll learn about generators, schedulers, tasks, continuations. These are new words that we'll learn to use. Conceptually, many of them have already been used, and we already had them. Even IOTA is a generator. But now with coroutines, potentially, when people talk about those terminologies, they will maybe mean the same thing. Maybe we'll better be able to understand each other. They also simplify and canonize some cases where there are multiple components that have very complex interactions among them. So some systems where there are a lot of components with very, very complicated interactions can be simplified with coroutines. So asynchronous systems, when events come in at different times, or state machines that are very, very complicated. And sometimes, or another use case is massive concurrency. We need to have a very large number of operations that need to happen sort of like in parallel. Without coroutines, implementing those could be very, very complicated, and will sometimes need us to sort of like meld together the functionality with the structure and the I guess wiring between components. And coroutines can sometimes help with those types of things and make them simpler. Another thing is that they support different code organization. As I mentioned with lambdas allowed us to put pieces of code that relate to each other closer. It's similar with the coroutines, because coroutines actually differentiate the code locality from the execution locality. So I can have several lines of code one after another in a coroutine, and they actually have them run in very, very different times along the lifetime of a system. And that can sometimes be very confusing and sometimes make things easier, but that's the power that they give us. We should make sure to use it and not misuse it. And another thing is that with this type of separation, we also get the ability to more cleanly understand what is like action logic or business logic, and what's just the execution policy or the framework within which we want the logic to run. So I'll focus in the talk more on how we write coroutines and when we write coroutines, and less about the generated binaries that actually gets turned into that. Basically, the C++20 language and various coroutine libraries, some of them are going to be added to STL very, very soon. Some of them are still not there, but they're in charge of a lot of the heavy lifting. And in this talk, we'll just take it for granted that they know what they're doing and just learn what they provide us when we write applications. Okay, so let's switch back a little bit to just fundamentals, just to make sure that we're all on the same page on what coroutines are, a little bit of basic terminology. So first of all, in terms of history, for C++, coroutines was added in C++20, as we know. And again, it was only added as a language feature without library support. Library support is just going to start coming in C++23. And technically, a coroutine is a function that can get suspended in mid-execution and then resumed later on, right? In C++, a function will suspend or can potentially suspend if it calls the co-yield or co-await keywords. And then each coroutine has a handle to it, which one can use in order to resume it later on. Okay, so that's the basic idea in a nutshell. And this notion is quite old, and it seemed like it was abandoned in the industry and the community for some time, and then it was reborn. So in the 50s, in the 60s, in the 70s, there were languages that had coroutines, and coroutines were used and was quite popular in several systems. And then it seems like there was a decay. There weren't many new languages invented with coroutine support. And I think there are some reasons for that. A lot of it has to do with better hardware, better multi-core hardware, and like a rise in popularity of threads. But then in the 90s, it seems to have been like a reawakening. So in the 2000s, C# added generators, the D language, Python, Kotlin, Scala all added coroutine support. Then in the 2010s, C# had like a next generation coroutines. JavaScript, Rust, Go added them, different kinds of coroutines, but they were all added. And then finally in 2020, C++ also joined the bandwagon, and we have it with C++ as well. So let's think a little bit about what does it mean to have a function suspend in mid-execution only to be resumed later on, okay? So basically, what we need is to save our state. Okay, what's our state? What's the thing we need to? Yeah.
Can you elaborate on the difference between a coroutine and a thread from this point of view?
Yes, it'll be, I think, more apparent later on. But for now, let's just say that a coroutine is just a function that can get suspended. Okay, a thread is also something that can get suspended, but a thread is something that is more general. It's typically like a hardware resource. It's something that is it's larger and more general. But I will get to it a little bit later.
I didn't know about coroutine, so I'm trying to understand. And like from what you're telling, it looks like they seem a sort of managed.
Yeah. So bear with me for a few more slides. I think maybe it'll be clear. And if not, let's get back to it. So what do I need to save when I suspend a function? I need to save all the local variables, right? I need all the arguments that I received. If the machine had some state that's not really in a variable, like temporaries that were pre-calculated, maybe even registers, and the exact suspension point, the exact point where we need to get back to resume from, that all needs to be saved. And potentially, once the function ends, it needs to get back to its caller. So I need to also save the return address where I might want to go if once the function, after being resumed, gets executed until completion. Okay, so this, I think, probably looks relatively, I guess, familiar to you, because every function call that happens today in C++, even before C++ 20, is actually a suspend resume, right? Because I'm inside a function, I'm inside of a caller function. I want to call another function, so I need to suspend whatever I'm doing, let it do its job, and then wait for it to complete and resume, right? But it's less general. Right? Whenever I suspend in a function call, I jump to the start of another function. I don't jump to anywhere else. And a resume only takes place when the subroutine finishes, and then it gets destroyed. Okay. So basically, the suspend resume order is in a last in, first out manner, right? And that really lends itself to a data structure, which is the stack, right? And for that reason, you probably know or these components seem familiar because even like since I guess the 60s or maybe the 70s, we know about the notion of the stacks, where in this case I'm presenting like subroutine A calling subroutine B, calling C, calling D, and all of their information. And while subroutine D is currently running, A, B, and C are suspended. Their state is being stored in what's called a stack frame. Okay, and every stack frame basically holds, as I mentioned, the local variables, the temporaries, some bookkeeping information, the return address back to wherever we stopped B, etc. So that's the basic idea. And this stack structure is very, very convenient, very nice. But as you mentioned, it's very rigid in the sense that whenever we want to suspend and go somewhere else, we typically go to the start of another function. And whenever resumption occurs, it's coupled with the destruction and completion of the subroutine itself. Okay, great. So coroutines basically need the same information, but they need extra flexibility, right? So the extra flexibility is that when I suspend a coroutine, I don't have to jump, or I don't typically jump to the start of a different function. I typically either jump to and resume another coroutine, or I jump back to my non-coroutine caller and resume it, even though I'm somehow suspended in the middle. So that's the idea. And we're basically decoupling the operation of creating and destroying the stack frame from the execution flow. So stack frames can get created and destroyed in a totally different flow of operations compared to which function is currently running. And that way, for that reason, a simple stack just doesn't do it, right? And that's where different languages implement coroutines differently. We have one set of languages that go stackful and others that go stackless. I'll save you the trouble and remind us all that C++ is stackless. So the basic idea is with the stackful implementation, every invocation of a coroutine potentially creates a new separate stack. Okay, and the operation of the coroutine itself and every function that it calls afterwards actually runs in that separate stack. And the act of suspending and resuming basically involves sort of like storing that stack aside and jumping back to the original stack or moving from one stack to another. And in that sense, stackful coroutines are very, very similar to multiple threads, except that with multiple threads, we have separate stacks, but where each of them can run in parallel, or where the operating system can decide which of the stacks or threads of execution with its own stack it runs. With stackful coroutines, we typically have one single thread, or at least the operating system doesn't really have much control over it, and it can basically choose and jump from a few stacks as time progresses. Okay, but as you mentioned, another thing is that stackful coroutines are sometimes or have similarities to the notion of fibers or green threads, if you've heard of those.
But in that case, like when two sides went to execute like one stack or the other, is the scheduler or the operating system, or how is that?
Yeah, that's a good question. I'll also address that later. The decision is basically done by us or by the coroutine library. I'll discuss it later. There's a lot of flexibility there, and we'll talk about it. Yeah. So so stackless coroutines are where we don't have extra stacks. Okay, so the coroutine frame that doesn't live inside any stack. It just sort of like hovers somewhere in memory or somewhere in the heap potentially, and doesn't have any like anchor to lean on potentially. It's just so every coroutine we create just allocates a stack frame somewhere. Okay, or we call it a coroutine frame, and from there we need to understand how things happen to work. And the first question that one typically asks is, okay, so let's say I start a coroutine, start executing it, and it wants to call a function. Okay, so if it doesn't have a stack, if it's not in the stack, where does the function go? Where does it go? Okay, and the answer is that it goes into the same stack, the one stack that the system has. Okay, so this is how the world look, or a memory layout it might look in a world where there's a coroutine. And in this example, subroutine A called subroutine B, and then subroutine B wanted to call a coroutine C, and the coroutine C wanted to call subroutine D. Okay, so the entire state of the program has some small stub on the stack, but most of the frame is out of the stack. And at this point, subroutine D is the one that's running. The coroutine is suspended. A and B are of course suspended as well, and the stub is what makes it so that when subroutine D completes, we'll jump back and resume the coroutine at the point where it completed. Okay. Now the thing is that so if we look at it, we understand that when subroutine B wants to call a coroutine, first of all, there is some allocation that needs to be done if it's the first time that the coroutine is generated. But if the coroutine is already there and already allocated, resuming it is very, very similar to like a virtual function call. It's an indirect call into some location where we can go and run from that. And as long as subroutine D is running, there's actually no way to resume a coroutine C because it's still waiting for D. There's no way to get it to completion because it's sort of like has its stub stuck inside the stack. So the only places where we can really truly suspend a coroutine is when it's on the top of the stack. And there's also this nice notion where when a coroutine decides to suspend itself, when it's on the top of the stack, it can either resume B or go and resume a different coroutine like instead of itself. And in those cases, typically, it will be just one single stub, just switching from one coroutine frame to another. Yeah.
Yeah, and I was going to ask, so like if a coroutine calls another function that is itself a coroutine, do you then just get another coroutine stub and a second coroutine frame is allocated dynamically? Yeah,
so the typical thing is that to call another coroutine is typically to allocate it somewhere else, and then we need to somehow suspend the calling coroutine and resume the called one. And typically you can do it while keeping the same stub. So in that case, that second coroutine can go back and resume the first one and so forth without hogging the stack.
And that would be if you did like a co-await or...
Yeah, but the way to do it is a little tricky because in general, the return address is typically something that's kept in the stub. So the secondly called coroutine will not really know how to get back to the coroutine that called it unless we do something specific to it, and that's where co-await will come in. Okay?
Just to clarify, subroutine D can't yield, right?
Correct.
Okay.
Correct. If any function that has a yield keyword is a coroutine, right? So it's not its frame doesn't live on the stack. Okay, great. So now let's talk a little bit about the mechanics of how it's done in C++. Yeah, I have to say that this is not my graphic. It's from Kevin Henney. You have the slides. Go to his talk. The talk is not just about coroutines. It's so mind blowing. I had to share it with you. So yeah. Okay, so let's see what the terminology is in C++ for coroutines. So we talked about the coroutine frame already. That's a notion from the C++ language where we keep the state of the coroutine. There's also a notion in C++ of a promise. Okay, the promise is sort of like the controller of an object of coroutine. Whenever we create or a coroutine frame is created, a promise is created with it. Okay, and every coroutine knows what's the promise type that relates to it, and it's meant to control the coroutine. It's what is able to decide whether the coroutine will get suspended or resumed on different occasions, like right when it's initialization or right before it, or what happens when it ends, whether and how to handle the cases where a coroutine yields. The promise really takes control of a lot of that. And it does that by implementing these different functions like initial suspend, final suspend, and yield value. Okay, so initial suspend is called right after a coroutine is created and the promise with it to let the promise decide what to do next. Similarly, whenever the coroutine calls co-yield with a certain value, then the system goes to the promise and calls yield value, gives it the value, and lets it decide what to do with the value, and also whether to suspend or resume the coroutine itself. And the promise gets created and destroyed with the coroutine. I sometimes think of them as one big object, and I think in other languages that are more object-oriented, perhaps we could have thought of the promise as sort of like a class that maybe derives from this coroutine frame that the compiler generates for us, because they live together and they're typically aligned in memory right after another. Then another concept that we heard about already was coroutine handle. That's sort of like a pointer to a coroutine frame, and it's an accessor. And the main things that we can do with it are either to resume a suspended coroutine or to destroy it. Okay, and there's like a bidirectional relationship between a coroutine handle and the promise. So if I have a promise, I can typically very easily create a handle for that same frame. And if I have a handle, I can quite easily get the pointer to the promise itself. And then the last major term of trade that you should know about is the return object of a coroutine. Okay, and the return object is sort of like the caller-facing API of a coroutine. Okay, so you know obviously that when I write the code of a lambda function, it looks like a function, but it's actually an object, right? And I can assign the lambda to a variable, and the variable is an object of some unknown type. And similarly, if I define a coroutine that has a return type, that's like an object, and it's not the object that gets returned when the coroutine ends. It's actually the object that gets created and given to the caller right when the coroutine gets started. And that's sort of like the API. Once I call a coroutine function, I get that return object, and its public API is the API that I'm expected to use when I work with the coroutine. The basic idea is that this resume and destroy mechanism is considered too low level. Yeah,
Does it mean that the coroutine can return a void?
Correct. Well, like the coroutine, when it completes, it can potentially not return a value on completion, but on the declaration of a coroutine is a function that has to return an object. I'd say that there are some ways to do that as well, because I think there are ways to specialize or say that the promise type of a function that returns void is some specific object, and then that promise type can still be used, but it's relatively uncommon. The typical thing is for the return type to be that. And
I was picturing a scenario where you want to use a coroutine to, for example, facilitate some data processing of some time that was ending up somewhere else, and maybe you didn't really necessarily need to have a return object for that.
Yeah, of course, but we'll see it.
Okay.
The thing is that when I call the coroutine, it doesn't really start my code. It doesn't really run the code of the coroutine. It just creates everything and gives me this return object where I can go and work with it. So So because coroutines are meant to represent some higher level notions, that's where the API object comes in. It has a public API that is different than just resume and destroy. So when I work with a coroutine object, I'm not expected to work at this very low level, and I'm not expected to even know that this thing that I have in my hand is actually a coroutine. I just look at it as any other object. And a good example for that is a coroutine that just sequentially calls co-yield and yields one value after another, where I would want it represented to the caller as like a range, as like something that I can iterate over, can start from its begin to an end, and do like a plus and a dereference operator. And that's exactly what the generator that we're getting in C++23 is going to do. So the generator is something that I could put as a return or the return type of the coroutine, of a coroutine that I write, where in its body it co-yields very many times, and whoever calls that function receives the generator and can do like a range for loop or something like that to actually get the function to resume and start yielding values, etc., etc. Okay, great. So the last notion that I didn't speak of that you should know is the notion of co-await, and basically handing out the control of whether to suspend or resume to someone else, and not just to my promise. So co-await allows a coroutine to basically consult with another object on whether I should suspend now, whether I should resume now, and also to communicate with some other component. Those objects are called awaitables, and when I call the co-await operator them, I can generate, or I can have awaiters. Okay, and the awaiter is sometimes the awaitable is an awaiter, but that's like a implementation detail or something that's subtle and sometimes should be used and sometimes shouldn't. The thing is that the awaiter is basically what can decide whether this is a good time to run the coroutine that is now co-awaiting me, or whether it should get suspended because information is not ready. And once information is ready, then the awaiter can pass that information back to inside the coroutine as sort of like the return value of the co-await. So the awaiter basically implements I think two main functions, await ready, which will return a Boolean, or three main functions, sorry. Await ready, which can basically try to understand whether this is a good time to resume the coroutine that's waiting on it or not. Await suspend is something that implements and to get notified that some coroutine that is waiting on it just got suspended, and it receives the handle to that suspended coroutine as an argument, and we can store it and use it however it likes. The await suspend, you can see it can return either void or bool or a coroutine handle on its own, and that has to do with the fact that sometimes when we suspend one coroutine, you might want to resume another coroutine, etc. So this await suspend functionality handles that, and the awaiter has the power to decide what to do next. And typically you just need, or you actually have to implement only one of those. You can't, and you can choose whether to do the void case, the bool case, or the coroutine handle. I won't dive too deep into the details unless you ask me later. So the last main function is the await resume, which is called whenever we decide to resume a coroutine after it is called co-await. And keep in mind that even if await ready returned false, meaning that we don't need to suspend, then there's no need to call await suspend, but await resume will get called, especially in order to pass in some return object, some information back into the coroutine so it can be used. Okay, so that's the basic mechanism of how a coroutine can interact with some external system or mechanism or component that will control whether it should suspend or resume, and can pass information back to it once it gets resumed. Okay, cool. So this is like, again, an example memory layout that also incorporates the C++ notions. So what I'm trying to capture here is the case where subroutine B is called some coroutine C, and coroutine C is just about to get suspended. Okay, so subroutine B will typically have the return object, right, the API, and inside the return object there will typically be a coroutine handle to that frame. And the object will not interact, and the subroutine will not interact directly with the handle. It will interact with the return object. And then the frame itself will also have this promise attached to it, and the promise is where some of the decision making is done. And as one of the temporaries, if this coroutine or just called co-await will have the awaiter that was returned, and that awaiter will remain living here inside the frame for as long as the coroutine is suspended. It will be used once we decide to resume. Okay. So in this situation, for example, we're just about to call the await suspend on the awaiter, and that await suspend will basically need to decide what to do next, whether to go back to coroutine B and resume it, or to just resume coroutine C because everything is fine, it knows what object to give it, or to just switch control and resume a different coroutine on its own. Okay, so that's the basic way that these things work. Questions about that? Okay, cool. So we've gone through our introduction, and now we'll try to go over a few scenarios where people typically use coroutines, both in C++ and also in other systems. And my basic idea is to, first of all, give you a little bit of a hint of typical types of problems or typical types of systems that you can see, you might see in your workplace or might see like in your career or in the future, where you could think, hey, I have something like this, maybe I want to use coroutines for that, etc. And also, I try to give a little bit of some understanding of how the different systems that might be implemented inside them. So first up, as probably you could expect, is a generator. We already talked about a generator. It's a function that returns many values using co-yield, and we look at it as if it's a range, right? Another way to look at it is a lazy range, right? Because it only gets resumed once or one time after another when new information is required. It doesn't need to generate a full sequence in advance, only when it gets asked for. Okay, so that's the idea. So obviously the generator needs to look like a range to the outside, so we will implement an iterator and a sentinel and a plus operator and a star operator. And this is like a short example, like the mandatory Fibonacci example, you know. The class, the function, as you see, its return type is a generator, but as you mentioned, it's just the API. And in this example, I wanted to not to write the shortest form of a Fibonacci, but I wanted to show that you can call co-yield several places, like many times around the code. You can call co-yield inside a for loop or outside a for loop, etc. And whenever the co-yield gets called, in case of the generator, then again the generators it has a promise, and that promise yield value function will just store whatever got yield inside it, so that the next call to the reference operator will return it back to the user. Yeah, go ahead.
So it's the generator, like in this example here. So the STL itself is implementing the promise object and everything for us. Is that correct?
Yeah, the
Okay.
STL is implementing the return object, the promise object, everything.
Okay.
Yeah.
Cool.
Okay, the relationship between the return object and promise object is typically very, very tight. So basically, by declaring that I return a generator, the generator will also tell me what's the promise that works with it.
Yeah, I have a question. So, what's the difference of just writing a regular function and having like A and D be static variable?
So technically, there's not much difference. One could go and write a Fibonacci generator without coroutines. We could create a class that has two member variables, A and B, and those member variables A and B, and this class could implement the begin, or I guess some iterator type of API, and it could work just fine. Another example, for example, is ranges iota. Okay, ranges iota simply without coroutines, but conceptually it is a generator. It's also called a generator in most parlances. And now in C++23 we could, if we like, rewrite iota as a coroutine. I'm not sure we want to do that, but the differences are very, very minor. Yeah.
We could instantiate different instances of the coroutine that would have separate state, unlike a static threadable static, right?
Yeah, that's correct. Like so yes. So just to be clear, if you call Fibonacci sequence multiple times, every call will create a new frame, and that new frame will have its own set of locals, its own promise, its own generator, etc. Definitely, but
What if it was a class? The same
Yeah,
thing would
exactly.
but
happen.
still,
It doesn't
if
even
one would have
matter,
wanted,
maybe.
yeah. So I didn't understand the question, but I think now it's all clear. Great. Anything else? Cool. So now next scenario, which I think was alluded to before, how do we compose coroutines? Okay, so let's say we have a coroutine which is very large. I want to split it up into several other functions. Okay, I want to split it up because logically it makes sense, but splitting this up means that I need to deal with the whole notion of the stack, right? And what happens if one of my sub components wants to suspend? So how do I do that? That isn't trivial in a stackless world, right? So the basic idea is that I want to make sure that if I call another subcomponent of my own and want it to allow it to suspend instead of me, it should also need to be a coroutine, obviously. And I want it to sort of like, it's again, to suspend myself and resume it as if it's at the beginning, like a regular function call. And I just want to make sure that when it gets to completion, it will get back to me just as if it's a function call, although there's no stack, right? So basically that's the idea. The caller, we want to create a coroutine frame, suspend itself, start that other one, and the callee should know to resume whoever called it once it's complete. And basically this notion is known in coroutine libraries as a task, okay? And under the hood, a task is actually a coroutine return object that is also an awaiter, okay? And let's see what that means. That means that when I create it, I can also suspend and let it run because I can run a co-await on it, okay? So the caller will co-await the task, and that co-await operation will choose to suspend the caller. It's a wait suspend call. We just store that caller's coroutine handle inside itself in order to know where to go back once everything complete. And this stored handle is called the continuation, okay? And then the task's final suspend, when it knows that the called coroutine got to completion, it will know to resume the continuation to have a sense of something that is like a stack, even though we're not living inside a stack. Okay, and obviously the task also needs to deal with exceptions. The entire, exceptions also have a notion of stack unwinding. If we don't have a stack, we can't do stack unwinding. So tasks need to do all that by itself. And essentially, what this thing gives us, doing composition of coroutines in this way, is sort of like a linked list of the stack instead of what would usually be a stack. Okay, questions about that? I think many times when people are dissatisfied or less satisfied with stackless coroutines compared to stackful ones, it relates to these types of things where you find yourself having many functions return tasks of T's instead of T's, and creating all these linked lists that can get lost.
Yeah, I was about to say, so this essentially means that we have to dynamically allocate every frame for every coroutine that we co-await on, essentially. So I assume this means that really the use case for this is some situation where you would otherwise be blocked for some non-trivial amount of time that is going to be more expensive than the allocation itself. Like if you're going to be waiting on IO or to acquire a lock or something. Yeah,
so first of all, yeah, I think you're right. But the main use case that I can see for continuations is just the ability to compose things. Take a few coroutines and have one call each other in a reasonable way in a world where there are no stacks. When it comes to cost, there are certain ways and mechanisms to try and alleviate the cost of allocations, but I won't go too deep into that. Okay, cool. Next scenario, async IO. Okay, that's also a pretty common scenario where people think of coroutines when they go and deal with them. And the basic idea in terms of implementation is to have the operating system or some operating system related library provide some awaitables. Yeah, like an awaitable that represents a socket or a file or something like that. And here's another obligatory example where I'll have an input socket and an output socket, and I want to read some bytes into a buffer. And then only once the buffer is full, I can go ahead and write it to a different socket. And only once that write operation is complete, I know that the buffer is ready for reuse, and I can go and do this entire loop at another iteration. And as you can see, this code looks obviously like a loop and like a instance loop, but the key thing is that those async read sum and async write functions, they do not actually block, they suspend. Okay, so those are awaitables, and the awaiters suspend this coroutine that's calling them, giving the thread, giving the system the opportunity to do something else. Okay, and the basic idea is that once they're called, they suspend the coroutine. They give the coroutine handle and store it somewhere that's close to the OS, I guess, and register. Ask the OS, please wake me up when the data arrives or when the operation completes. And then that callback that the OS calls is able to put the results wherever it needs to and resume the coroutine. Okay, so that's the basic notion of this scenario or paradigm. And typically there is some notion of an IO service, which will be an object that will sort of like take control of the execution thread or the main loop, and that's and that IO thread will be like the object that sort of like manages the entire show, and it like binds an actual execution thread to the operation of all these resume and suspend operations taking place. Okay. Questions about the asynchronous IO scenario? Great. Cool. So next scenario, massive concurrency. Massive concurrency is when we want to have concurrent execution of potentially many actors or algorithms that might run for a very, very long time. For example, if we have like non-playing characters or AI characters inside a game or a simulation, or if you want to maintain a complicated network protocol with many clients when we're writing a server. Okay, and these types of scenarios, we prefer to think of our code as concurrent, where many processes or many states are running in parallel. But if you want a really large number of these operations to occur at the same time, the cost of each of them becomes very important. And the thing with coroutines, especially with stackless coroutines, is that they are very, very cheap. Okay, so they're cheap to threads. They're cheaper than fibers even. So it can be very, very easy to create tens of thousands and even more such coroutines that sort of like work as independent actors that get their own time slices. That's the way that they could be used. You can get a very, very massive, like sort of like a sense of concurrency.
Yes, just still don't fully understand like who assigned the time slice. Do they inherit the time slice of the parent thread, or do they have their own time slice?
Cool. So I have exactly a few bullets for you. Okay. So that's where a new term gets added to our dictionary, which is the scheduler. Okay. So a scheduler is typically an object that again acts like an awaitable, and all the actors are expected to co-await it regularly. Okay, to basically give up or let the scheduler give the scheduler some opportunity to suspend them to give someone else the opportunity to run. Okay, and there are other ways where the actors can co-yield back to their promise, and the promise will handle all of this. But typically, there's a scheduler object that does that. And what you would typically do is you would give a single thread or maybe several physical threads to the scheduler. And that scheduler will basically run the show and decide which of the actors to resume at which point. And whenever you resume an actor, the actor will have to await back to the scheduler to give the thread back to basically continue, let others have their time in the sun as well. Okay.
Am I correct if I get similarities here with kind of user space threads, if you like?
Yes, that's true. When we talked about green threads, that it's very, very similar. And again, the user space threads are also called fibers sometimes. And again, stackless coroutines are even cheaper. Okay, so for this reason, where we rely on the actors to co-yield, that's why many times this type of scenario or paradigm is also known as cooperative multitasking. Okay, because it's cooperative, because if one of the coroutines, one of the actors decides to just hog the CPU, there's not much that can be done.
So just to clarify, when we say cheaper compared to fibers and threads, we are referring to the act of suspending and resuming, correct? Not like allocation and deallocation of the coroutine frame.
All of it.
All of it is faster.
Because allocation of a thread is like an operating system event. You know, it's much more expensive than even like a malloc, like allocating a frame on the heap. Okay.
And I assume you don't have context switch, right? When the moment they
Yeah. There's no context switch on the OS level. You don't need to really save register it's not. There's no notion of where a thread gets interrupted in mid operation, and we need to even store like state registers and sign bits, etc. Because it's all very cooperative. You know exactly what needs to be stored and what doesn't. Okay, and again, so obviously creating a thread is much more expensive than allocating memory. Creating a fiber is also more expensive than allocating just a single frame, because a fiber is typically like a large stack that needs to be pre-allocated.
So the actors and algorithms don't necessarily need to be relatively too long running in order for us to already realize benefits from using coroutines. Is that correct?
Yeah.
It says long running actors and algorithms.
Yeah.
So,
Yeah, definitely. I guess. But a typical scenario is where they're long running enough that it doesn't make sense to just run them to completion, right? If they're also running, we can just run them to completion. But yeah.
So then, what's the when should we not use coroutine but use thread? So
I have obviously a few slides on that as well. But coroutines, they do add some complexity. You need to understand what you're doing with that. That's one thing. Secondly, scheduler and scheduler objects are not very trivial. I typically would not expect any of us to implement schedulers. If we use coroutines, happily there are coroutine libraries that have already implemented schedulers. But I assume that most of them are not as good as an operating system scheduler. So that's one thing. And then another thing is that again, making the most use of all the hardware resources, etc. Sometimes a little bit of cooperation with the operating system can help. Yeah.
But that can be even a good, strong advantage, I must say. Like if you have very specific requirements in terms of when to run some specific task, you can develop your own scheduler and kind of allocate more threads to it, or more resources, or more time.
Yeah. And as was mentioned before, the preemption aspect of versus cooperative aspect of threads versus coroutines can also sometimes be impactful and important. Yeah, go ahead.
Yeah, I was just going to say the centered receiver, which is in flight, hopefully for 26, provides scheduler concepts, interfaces, hopefully some implementations, and that works with coroutines.
I was just going to say, I suppose another potential downside or risk is just that in a very large code base or something, because it is cooperative multitasking, if somebody doesn't get the whole situation, they can easily add a new kind of liveness issue where essentially every other coroutine is blocked.
Definitely. The biggest risk of these types of situations is not that one of the actors is really decides to get out of control. They just happen to sort of maybe go and make a blocking call to the OS, right? And suddenly everything gets halted. So yeah.
No, the biggest issue is that if the coroutine is suspended, your entire state is off to the side. Like in your Fibonacci sequence, if you did a class, you would have two members, and that would be the state. And you wouldn't give out the pointers to those two members, but in a more complex, you had a class, and that state would be visible, while the class is not active, member functions aren't being called. That state is addressable. Somebody can, access that state through hopefully member functions of the class, but they can access that state. When the coroutine is suspended, whatever you returned is the only thing you can address. All your local variables are moved off to the side. Pointers to them have been invalidated. If you happen to give out some of those, you're in the world of hurt.
Okay, so you're comparing and contrasting a coroutine implementation versus some non-coroutine implementation of actors.
Yes.
Okay. That's correct. Again, sometimes a return object of the actor can have its own API, and there can be ways for the coroutine itself to share some of its local variables with the promise type in order to have the return object get more access into the frame. But I guess it's not a typical use case.
But not the local variable. Whatever you give out during co-yield, that's it. You can't give out pointers.
Yeah, I'm in co-yield, but if a promise type has pointers into my coroutine frame, I don't think there's much issue in reading that. But I don't know.
But how would you get them? They were your local variables. When you ran, they were your local variables.
Yeah, but then I can give pointers to them basically to my promise by co-yielding, or actually like the coroutine has control of. I don't think it's something that would be very encouraged, I guess. So definitely, if you want more visibility into the internal state of an actor, then the coroutine approach might not be the best suitable. Great.
We do this all the time, yeah, but all your variables actually reside in the coroutine frame allocated dynamically in a heap. So as long as your coroutine frame has not been destroyed, you're absolutely fine.
Okay.
Frames do not get relocated.
Okay, let's look into a few more scenarios. And again, once we started thinking about scheduling, we can think about more advanced or sophisticated types of scheduling, right? So one way is to perhaps think about priority, okay? Where the scheduler is aware of various actors running, and each of them can be of different priority. And it's not just that every different actor has its own different priority, but even as the coroutine is running, it can change its own priority. So I can get invoked or resumed, do my only most critical part of processing, and if I have some cleanup to do later on or something else, I can decide to co-yield back to the scheduler, tell them, hey, my priority is going down, I only have some cleanup to do, and then the scheduler can decide when to resume, when is a good time to resume me for actual cleanup. Okay, so that's another operation. So with the co-yield operation, or maybe a co-await to the scheduler, I can specify what's my priority, and the scheduler I can really switch between priorities as I'm going. Another sort of like fancy type of execution is batching. Okay, so again, a scheduler can know perhaps that several different coroutines are looking or waiting for the exact same information or for very similar information. So it can basically see that they're all suspended. It can look for all the information that they want. For example, go to a database, fetch it all in one big batch, and then resume them all at once without having to suffer the entire round trip for each and every operation. So that's another nice use case. And again, when you start working with all these things that you think of as threads, and you have a scheduler that needs to sort of like implement what an OS implements, you start realizing that you need some coroutine friendly versions or scheduler friendly versions of things like mutexes, barriers, etc. Because again, whenever an actor is resumed or whenever a coroutine is resumed in this type of a framework or a model, we don't want it to ever get blocked on the OS. But still, if I want a complicated or a complex system where there are shared references or where I do need to grab a mutex and make sure that no other actor does something, I need to actually consult with my scheduler, do some sort of like an async lock by letting the scheduler know that it should suspend me and only resume me once the resource that I'm trying to lock is available. So this is another type of complexity that more advanced schedulers can provide and can give us a better sense of sort of like a really massively concurrent system with all the bells and whistles around it. Okay, great. Next scenario, switching execution environment. So another nice thing with coroutines is that once we suspend it, we can actually resume it in a different thread. Okay, and sometimes that can be beneficial. Okay, so one very prevalent example is if I have like a UI thread and background threads, and some pieces of code have to run on the UI thread, I can still have one function with only snippets of code that can just need to run on the UI thread. So I can again go to my scheduler or go to the system and ask to get suspended, get resumed in the UI thread, and then maybe get suspended back and resumed back in the background thread, where again the entire logic of the code doesn't have to be broken up into different events or different subcomponents as a state machine, because it can all look like a nice flow inside a single function where there are these calls to be suspended and moved to a different environment. Somewhat inspirationally, maybe there are ways where one could switch from a CPU to a GPU. It's a little far-fetched, and maybe in the future where standard would think of things like multi-server clusters, we can do even more things, but not at the moment. Another type of switching between environments has to do with, for example, looking at massive data sets in parallel, where I would want where I have multiple threads accessing a very large like data set or something, and I am afraid about the concurrency issues. So instead of having each of the threads run their code and lock whenever they lock whatever they need when they access it, we can divide and conquer. Divide each running thread to be in charge of a different part or a different shard of the entire data structure, and a coroutine that needs to access some information from one location and some from another can potentially, in some cases, can be beneficial to just suspend the entire coroutine and switch over to the thread that is in charge of a different shard, etc., etc. Yeah. So, and again, this is probably typically mostly useful when most queries only require a single shard and not others, but it can potentially alleviate the need for the threads themselves that are in charge of those different shards to call any lock operation and to block any of them, or to have any fine-grained locks on the data itself. Obviously, the task of distributing and moving around the different suspended coroutines from one thread to another and managing this thread pool might have some locks on its own, but that's the scheduler's problem, right? Okay, so that's this scenario as well. Last positive scenario is task graphs and senders and receivers. We already heard of them a little earlier. So the current vision for of the committee for concurrent algorithms in STL has to do with the creation of these execution graphs, these objects that basically pass information around from one to another with some splits and joins in the road, etc., to create these very composable mechanics of large-scale systems that are composed of smaller systems and can run highly efficient algorithms, both on CPU and on GPU. And that vision has the notion of senders and receivers. A sender is a component that's part of that execution graph that can basically generate sequences of information. It can also work as a link between in the graph with some input nodes and output nodes. And the receiver is the component that can get notified when new data is available and start the entire chain if needed. I'm not an expert on senders and receivers, but you're very welcome to listen to some talks by Eric Niebler, and there's a slide I took from him a little later on. And the basic notion is that typically an application will create an entire task graph of these sender objects that are connected to each other, and then the task graph could be given to some executor or to some scheduler, and that executor could have potentially a lot of information and knowledge both about the structure of the graph as well as maybe the machine or the system that I'm running on, and it could do all sorts of optimizations and define the best way to get that execution logic to run from start to completion. And the observation that was made by the committee is that awaitable types are senders and senders are awaitable types. So there's a lot of parallels between the notion of sender in the sender-receiver universe and the notion of awaitable types, those types that coroutines can co-await on. Okay, and for that reason, whenever we write a coroutine, we can potentially have that coroutine be part of these execution graphs that are coming potentially in the future versions of C++, and might ease the implementation of several sender-receiver types of algorithms. Yeah?
How can you build execution graphs in the presence of branching?
How do you build execution graphs in the presence of branching? What do you mean by branching?
Senders automatic can make decisions about what sender to send.
Yeah, but I think maybe the next slide will clarify something, but let's go to it.
Okay.
Okay, so I will say that the fact that coroutines are relatively lightweight and the fact that the compiler has a lot of information about the mechanics and the code inside the coroutine, etc., should hopefully give the compiler the potential to create some good performance and some good optimization when it comes to a graph where some of its nodes are regular senders and other nodes are just awaitables or coroutines. So this is the motivating example. As I mentioned, I took it from Eric Niebler's talk from CppCon 2021. Go ahead and watch it. And again, the thing is that, so for example, stood execution when all is a sender, okay? And that sender is actually a fork, not a fork, but a joint in the road, like where we can have two different senders, and it will wait for both of them to complete or something like that. And so we have these two coroutines that basically can behave because they're a task as if they are senders. I can connect those with the when all, and then I can have this entire function, which is a coroutine by itself, also co-await on that. And when it comes to precedence, I think the into tuple happens before the co-await, but I'm not sure. But I think that's the way that it happens. But basically, we see that we're creating this sort of like an execution graph where we have two async reads that gets joined into a single when all, and after that we'll pipe it into another sender, and that's the way that these things can potentially work. So, questions about senders and receivers? I assume you will all learn a lot more about them, as will I, as time progresses and as the committee gets more and more committed to them. Okay, so a few anti-patterns, a few ways or things where I think coroutines are sometimes used and perhaps should be reconsidered. And again, I'm not the true ruler. You can obviously outvote me, and I'd be happy to hear what you think. But basically, we should remember that just because something can be done with the coroutine doesn't mean it should be. It's like the new shiny feature in the language. And here are some reasons why not to do it. So, as we mentioned, coroutines basically break the code locality versus execution locality. Without the coroutines, lines of code that are close to each other on the source file typically run right one after another in real life. With coroutines, that's not the case, and it's sometimes very, very hard to grasp. Okay. As we mentioned, the exact performance of coroutines is something that is not mandated by the standard. Okay, the standard gives a lot of leeway to the optimizer to try and eliminate allocations, to reduce the size of the coroutine frames as much as possible, etc. But there's no mandate. The compiler vendors can basically do horrible things as well. So we should keep that in mind. And there are some horror stories, I guess. And then the entire interop, like between object lifetime, concurrency, error handling, is all a little bit different. As you mentioned, because we have no stack unwinding. Because we are very, very concerned about blocking the thread that we're running on, and not just suspending and returning control somewhere else, then any concurrency type of operations, anything that's blocking, is something that needs to be, taken a look at a very fine glass and checked out, so it can be the cause of a lot of issues and problems. And as we mentioned before, the whole viral nation of the continuation chains, the fact that once I start working with coroutines, I find that each and every function that I write needs to return a task of T instead of a T. When I just want to start a new project and I write a few functions, I don't know which of those functions might potentially want to call a coroutine in the future, or might potentially in some new iteration of our project be part of such a continuation chain. So I need to either think about it in advance, or and know that I'm some potential work is ahead of me for distributing those tasks across the code base. Yeah.
One thing that I've wondered about, I think that coroutines have incredible promise for making blocking operations a lot more efficient. But the thing that I've been concerned about is whether or not, in a very large code base that uses coroutines very heavily, is this going to become a fundamental obstacle for debuggability, essentially, and understanding control flow within that program? Is that something that you think just needs better tooling? If GDB was coroutine aware, maybe it would be easier for us to get a handle on that? Or I'm just kind of curious what you think.
Yeah, so it's a good question. And to tell the truth, I think that there is a lot of potential for tooling, especially once those concepts and notions enter the standard. Okay, so right now, there are libraries, we'll see them later on, that implement schedulers, tasks, continuations, etc. but they're not part of the standard. So none of the compiler vendors, none of the debugger vendors, etc., want to specifically optimize the development or debugging experience for those libraries. Once things get into the SDL, I think there's hope, and potentially the notion of a continuation chain is something that like a decent debugger could work with. I should also say, by the way, that Rust also has the stackless coroutines. There are other like popular languages with stackless coroutines. So this challenge on the ecosystem on dealing with them is not only a C++ type of thing.
I just want to comment on the previous question. Like, you got to establish yourself a decent baseline to compare things to. Like, of course, when you GDB a coroutine-based thing, you can barely understand what's going on because of lack of the tooling. But the alternative actually, you don't do things with blocking IO calls, right? We do it with a chain of deeply nested callbacks, where there's the kick off this thing and call this step function which completes. And when you lay out a sufficiently complicated program like this, you can get zero idea of what's going on around this either. So I think it's not perfect, but it's strict improvement over the current state of things.
I don't think at this point it is. When I started looking into coroutines, I've never seen that many ASAN errors. Like just how easy it is to violate lifetime with coroutines. I mean, ASAN finds them. Okay, good for ASAN. But how much in the totally innocuous code with coroutines violates lifetime errors? I mean, it's incredible.
That actually corresponds to not collecting the coroutines themselves, but to people not being able to use them correctly. So we are the very infancy of yet no decent set of do's and don'ts related to coroutines.
The C++ does you no favors here either, though. Lifetime is invisible most of the time.
Yeah,
you've grabbed a reference to something, bound it into your coroutine, and now you've if you're nested properly, it works fine. If you escape, the thing you're referring to is dead.
It doesn't work, and maybe if you're lucky, 1 out of 10 of those will crash.
and give you a crash that's point ship.
At least it will crash, but the rest will actually work until you run ASAN and it tells you, and then it also says, oh, by the way, you're using some weird stack unwinding. I'm not sure if I'm right about this.
Another thing is this complaint about lack of error handling subsystem. I would object to this argument because we do have this uncaught exception thing in promise type, so it's perfectly feasible to write an exception on a stack unwinding exception propagating mechanism using coroutines.
Yeah, and the libraries do it.
Callbacks.
Yeah, the libraries do it. The libraries typically are the ones that are mostly used around the industry. They do proper error handling, but still sometimes you need to understand how to use them. Yeah.
Is it possible to have custom allocators for coordinates?
Yes. So I mentioned earlier that one might think of the promise and the coroutine frame as sort of like a one big thing, and actually that is in many senses the case. When the coroutine frame is created, it's created along with the promise by potentially calling the new operator of the promise type, asking for the size of both the promise type and the coroutine frame. So one can implement their own operator, new operator, delete, etc. And good luck with that. Okay. So a common pitfall is just forgetting that there's another more direct approach to your problem. Okay, and one thing that really pops to mind is just textbook state machines. Okay, we have mechanisms, we have systems, we have boost state machine, we have state machine mechanisms, and yes, a coroutine can be implemented to work like a state machine, right? And jump from one place to another. But there are other ways that are sometimes more direct and more intentful. Again, if you use co-await and co-yield as some tricks to return different object types, because you want a function that sometimes return one thing and other times return another thing, it's not the intention. It's not what this thing was written for. So be careful with that, and try not to reinvent the wheel. Try not to write something that others have written. Specifically, schedulers are complicated. I do not expect myself and many people to write schedulers. I do use coroutine schedulers from CPP Coro or from libraries, much like I use the operating system scheduler. Try not to, sometimes one is tempted to start with a very, very simple scheduler that does what they want, and then they add in priorities, and then they add in synchronization mechanisms, and then they add in some I/O, and suddenly they've implemented an entire mini kernel. So be careful. Again, remember that this is still a relatively infant feature. The libraries themselves, even the ones with the most track record, are relatively young. So keep on the lookout. Look to see if there are any like issues found with those libraries that you've downloaded and used, and upgrade them. Look to see where the standard is going. And so again, to try and not find yourself 5 years in the future where you're using some library that's very, very different from where the standard has landed. Okay, cool. Another example of an anti-pattern is an event dispatch loop. Okay, so this thing like so what we're seeing, we're seeing like a while an infinite while loop that just co-awaits the world for some event and switches on the event, and that's the entire co-await in there. Okay, so this is like a typical event loop, and it sounds like very typical things that one would use with the massive concurrency scenario that I described before, right? But this is such a such an idiomatic case of an event handler, like an active object or these types of components that have already existed in the past, that I would encourage you to go and use what was already implemented and to be more clear. Okay, there are many such variations. And then one, I think, last pattern is splitting a function while preserving the local variables. Okay, if I have a very, very large function with multiple stages, and I suddenly understand that there are some specific points within that function where I might want to get suspended just in order to give someone else the opportunity to abort everything or whatever. And I don't want to split the very long function into separate functions with their own APIs, etc., because I just want to keep my local variables from one state to another. That might not be the best case, to just create your enum and just yield what stage you're in, etc., in order to sort of like have the compiler create that object with all those local variables, etc., etc. Again, because lifetime management of those of all those local objects is gone basically. As they are locals, they can either be, of course, destroyed with the entire coroutine or kept. But the entire time when this coroutine is suspended, we might not know what else is stored in there. So it's something that you might want to be aware of, and might actually try to do the old school refactoring of splitting up the function. Okay, yeah.
There's kind of continuous spectrum from this, which is like you never do this, to basically the Fibonacci thing, which just has two local variables.
So first, I agree. Second, I think IOTA and Fibonacci should not be implemented as coroutines. And third, yeah, it's a matter of taste. I'm not. You can overrule me on this. Yeah, it's a matter of taste, definitely. Okay, cool. So into summary and maybe a little bit more intuition. So coroutines are complicated. I chose to end with the anti-patterns, so we won't be too excited about this. So there are many new types of objects, many interfaces. It's not intuitive. Sometimes things are complex. There's, on one hand, there's a lot of hidden code or auto-generated code that the compiler does for you. But on the other hand, there's a lot of boilerplate that you need to do yourself, especially if you implement your own coroutine library and not use a coroutine library that's given with someone else. Again, these coroutines raise new concerns about object lifetime, about the cost of abstraction, about the quality of the optimizer. So we need to think about that. And it all looks so much simpler in other languages. But that's the way it is. But I should say it looks very, very simple in other languages. But it's more powerful here. And a few analogies again from other language features. So C++ 11 lambdas and C++ 14 generic lambdas. Again, when we first saw them, or when I first saw them, it was something new to grasp. It was a different type of beast. I knew that there's a lot of things. There are things that are happening like under the hood, a lot of hidden code getting generated. I needed to learn how to understand the whole notion of the lambda capture. I needed to understand what's the stood function and when is it fast, when does it allocate, etc. But still, right now we all use them. We all have learned the pitfalls, and we know how to use them effectively. The concurrency model as well, right? It's like a whole new dictionary of terms that we needed to learn, we needed to master. But once we're there, bugs are error prone, but so is performance. So coroutines are powerful in C++. There's potential of enriching our design language, having our conversation about very complicated systems be at a slightly higher level. We can talk with each other in higher types of designs. If it's done right, it does give unmatched performance. There are various talks giving like many examples where you can get either like massive concurrency with very, very low cost, or really, really fast implementations of like batch operations, or even masking cache miss penalties, etc. It's really, really nice when it's done right. The compiler is aware of everything. It can inline stuff. So there's a lot of potential for it, and as compiler generations improve, the potential can also improve with it. It's a gateway towards a simpler and safer concurrency. And by that I mean senders and receivers mostly, but also just thinking about concurrency at a different level. And again, some analogies. So I'll go back to STL containers. They're so powerful, and even for non-template experts, because it's all in the library, we just use them. Tuples, variants, ranges, they are so difficult to implement, but once you start using them, you just never turn back. And as I mentioned, the hard parts are mostly in the libraries. Most coroutines that I've seen, they reside in one of those common paradigms or scenarios that I've talked about. The return object, the promises, the awaiters, they're typically written once, and then you write many coroutines that use those same return objects, promises, etc. And there are already many open source implementations of all of these things. So CppCoro is a great library by Louis Baker. Unifex also has like a sender receiver type implementation. ASIO for mostly networking and file IO, etc. Corobatch does batches, and there are many more. Just look them up. So really, all that's left for us is just to use them and implement the algorithm, write the coroutines themselves, not the machinery around it. Okay, so I think that's pretty cool. Coroutines are powerful. Coroutines are complicated. The hard part is in the libraries, not in our code. So I'd like to thank you. Comments, questions, please.
What exactly does happen when an exception is thrown from a coroutine? Like, is it there's a callback on the promise or something, and an exception pointer gets passed in, or like how does it work exactly?
Definitely, there's a callback on promise, sort of like within the catch block. Mm-hmm. Like, so there is like a compiler generated catch block. Within there's a call to the promise, and the promise can cause it so that, for example, the continuations gets resumed with an exception thrown inside it. Okay. Yeah.
At some points, when can you clarify what you mean by scheduler in the context of coroutines? Like, is task and generator also considered schedulers, or?
It's a good question. I would say that the scheduler is basically like a mechanism where that should try to control when to or what to resume next, especially if various coroutines that are suspended are not explicitly waiting for some specific event. Okay, so but sometimes also if there are many coroutines that are waiting for some specific events, and maybe some of them wait for the same event, again, I would need some mechanism to maybe have my single thread or my few number of actual threads, resume them one by one. So that could also sometimes be considered a scheduler. But the typical case is when there are many coroutines that are ready to be resumed, then I need to somehow decide which one. What
But you could say the task is a trivial scheduler.
What?
You could say the task is a trivial scheduler for two coroutines. Generator is definitely not a scheduler. You can't wait on it.
Yeah. So again, it's a matter of terminology, and I think we should try to reach some consensus of what do we typically mean when we say task. What do we typically mean when we say an I/O service or etc. So or continuation. So yeah, you could say they're all like awaiters, receivers, etc. Or awaiters, return objects, and coroutines in the end. But we need to maybe rise our level of discourse. I don't know. Okay. Any more questions?
Yeah, I just want to get some more understanding on like how coroutine can make like a async I/O like much faster than just within a thread.
Okay, so the basic idea is that when you most I/O calls on most systems, you can either have them as blocking calls or non-blocking calls. Okay, if you're doing I/O with blocking calls, it typically means that there's some reasonable relationship between the number of those calls and the number of threads in your system. Okay, because whenever you create a call, a thread gets blocked. Okay, and having a system running many threads can sometimes be costly. Okay, so if you have a very large number of I/O operations that you want to do, and you don't want the cost of many threads, that's when you go for the non-blocking alternative. And with a non-blocking alternative, coroutines can make your code look a little nicer and look as if it was blocking it, although in fact
so
it's
by
not blocking.
non-blocking you mean so the I/O will trigger a callback from but in that case isn't it this perform similarly as just having the separate thread to run the callback? I'm just still not clear where is the time that's getting saved.
Yeah, so the thing is that there will be a separate thread that runs the callback. If you want to get a similar performance to like an asynchronous coroutine, what you would typically do is implement your own like a callback mechanism, and you will implement a class where this data buffer is one of its members, and it has two member functions maybe to maintain the state of the protocol, and you will register the different callbacks within it. Okay, and that class will typically will be maybe harder to reason about, harder to understand, compared to what looks like maybe a nice while loop, which might have breaks in certain situations, etc. So the performance compared to a handwritten state machine is probably negligible. But the bonus of coroutines is to make the code more readable. Yeah, go ahead.
A lot of times I've used coroutines or handwritten things that are basically just like that when I'm willing to trade off some latency for throughput too. It's way easier to, when you're doing asynchronous I/O, to just pick up with other work that you've got pending and get it correct.
But you can do that with threads too.
Thread, it's
But you pay the cost
more
for
work and
context
harder to get right.
change on threads.
Compared to the cost of like select, which would wake up your I/O, probably nothing.
No, but the thing is that the cost of a thread sometimes can be just the resource utilization. It's very easy to have tens of thousands of sockets or files open in the system. Tens of thousands of threads sometimes is more challenging, right?
Well, tens of thousands I would say is okay, but if you have millions,
Okay.
That's where it gets.
Okay,
like I
so-
wouldn't do it.
Millions.
It's also some separation of concern. Like a scheduler is hard to write, but you write it once and get a lot of eyes on it and get it right. Whereas if you're doing shared state cooperative multitasking, everyone has to pay attention all the time.
On the free framework does it, you basically have queues or buffers or whatever it is you're doing.
Yeah, I mean, it's like, this is abstracting a lot of that same technology in a way that's easier to focus on your logic rather than the infrastructure.
Great. Any more comments?
Sorry, I just wasn't. The question about allocation, I don't think that's like as crazy as it seems at first, because like it's one of the biggest costs. And if you like know what your algorithm is and you can do a read allocation, that makes a lot of sense for a lot of algorithms. So I was curious, what does that extension point look like? Is it a global extension point? Is it like a per coroutine?
So as far as I recall, every coroutine has a return object and a promise type, and that promise type is what gives you the ability to, you can customize its new operator. So you could, for example, re-implement the new operator for all of your task T objects. And then all of your coroutines that return a task T will use that new operator, for
I
example.
don't think
Part
they're
of the-
task here.
and-
They're on
yeah,
promise
but
T.
Part
maybe,
of the
yeah.
ugly machinery of coroutines is if there's an allocator parameter in the in the first position of your call that's creating a promise type, that allocator gets supplied to the construction of your awaitable type. The machinery's terrible to work with, but you can, you can supply the allocator that you want to the task or the generator without having to get involved in the overloading operator new.
Okay, I did not know that. Thank you.
Yeah, but it's ugly.
Yeah, my concern was mostly related to the use of this, let's say, paradigm in embedded systems. Like, for example, you would never use it if it has to allocate a stack, not a stack, but a coroutine in the
frame.
heap, right?
an
So
activation.
at that point, I would have a static allocated memory with a number of slots for my coroutines and just allocate it statically, and then I have an allocator that just picks a spot in constant time.
So so there's a lot of work and a lot of research on how to deal with the cost of allocation, and there are a lot of potential ways to either have the allocations done up front or to try and either make sure or give enough hints to the compiler so it knows that the stack is just fine in certain cases, where we have like a structured concurrency. And also, I would personally think that in many cases, coroutines can be a really good fit for embedded systems, because exactly because they don't have the resources for full-blown OSs. But I'm not an expert.
Yeah, no, sure, but there is the allocation problem though, that sometimes you just
Yeah,
cannot,
but
I mean, if you
I
don't
believe
know how
that-
long it's gonna take to have a memory,
Just keep in mind that you're not gonna allocate promise objects. Then allocate variable size coroutine frames containing promise objects as one of their like fields. So don't get any idea about like pool of objects of predefined size or whatever.
Okay, yeah, I'm speculating because I don't fully understand the mechanics of it, but yeah.
Yeah.
I have a question.
Yeah, you would, like reclaiming allocators would be difficult because the promise object, the waiter is somewhere in there, which you also know, but you don't know where it is. But the frame itself is whatever the compiler decides it is.
Yeah, it could grow, so.
Yeah, no, I should say that.
Oh, okay.
Yeah, one note that I should say on that.
But I don't know it.
But you have no way of
You've
knowing.
lost control.
It also depends on the frame.
Where's your gavel?
Yeah,
It's okay,
the
whatever.
back end figures it out, unfortunately.
Yeah.
So I do want to say that one decision that the designers of the feature went with is hiding information about the size of the frame itself. So, for example, with a Lambda, it's a very relatively easy task to look at the Lambda and understand its size, understand what's in its capture, and what information is inside the Lambda. Alternatively, if you look at a coroutine, you look at all the local variables, etc. It's not 100% clear that the size of the coroutine frame will just be the size of all the local variables plus some extra size for temporaries, etc. Because the designers of the feature deliberately gave the opportunity to the optimizers to be aggressive here and to try and reduce the size. And for that reason, different optimizers will create different sizes of coroutine frames.
If it's
Always be the
possible,
same.
but if it's possible to determine the compile time, is there any way, for example, to export? I don't know. Maybe I'm using the word terminology, but like a define where I can say, hey, I have this.
Like a size of.
Yeah, right. Size.
Well,
Yeah,
I don't know.
good one.
You can basically assert in your new, because you're going to get the size if you overload new. You can assert at that point, and your integration test will fail. You might even be able to static assert it. if
There's a
it's,
year waiting for you guys to argue this over.
Yeah.
Yeah, so there was another comment here. Yeah.
Yeah, so I just want it seems to be, this need an expert basically, right? If I have a big team, have a big code base, if I want to use coroutine, we have a lot of junior developers. They just try to learn C++. How does that organization adopt coroutine?
Don't dive
Okay.
into the deep end.
Yeah, the question of adoption is tricky, but yeah, as Chris says, you can make use of existing libraries. Try to take it in like step by step. Again, I don't have a lot of like from the field experience. Some people already come to your company with some coroutine experience from other languages, and that can sometimes be helpful as well. So, yeah. And I guess we're on time, so thank you very much.